How's it going, everybody? Today we have an amazing problem for you guys, right? It's a very, very interesting problem. So let's quickly go ahead and read the problem statement, right? So it says this is an interactive problem, right? Okay. So we're given a sorted array of unique elements, right? And an unknown size. You do not have access to the array, but you can use the array reader interface to access it, right? So you can call the reader get I, right? That will give you the value at the index, right, of the secret array, or return 2 to negative 1, 2 to 31 power minus 1, right? So pretty much integer max, right? If the number is out of bounds, right? So very interesting. So he says you are also given a target, right? Return index k of the array, right? Where the value at that index, right, equals target, or return -1 otherwise, okay? You must write your algorithm in log of n, right? So this is very interesting, right? So we're going to be given a reader interface, or a reader thing, right? That's going to help us in accessing the array that we don't now have access to, right? And somehow we need to use that array thing, right? Reader that's going to be given to us, right? To access the array, right? So by calling the API is given, right? So get I gives us the value, right? If it exists, if we're out of bounds, we get integer max, right? So very interesting. So uh so how can we solve this, guys, right? How can we solve this? Let's go through this example, right? So we're given this just this secret array, right? We're not giving it to a yeah, right? In integer target, right? And we can see that the number that they're looking for is 9, which is at index 4, right? So we return 4 as the index, right? In this one, there's no 2 in this array, which makes sense that we return -1, right? So yeah, very interesting. So how can we solve this, guys, right? Let's kind of think about the brute force solution, right? We're not going to do anything fancy or anything, no fancy tricks, right? The intuitive storage solution, right? Would be to do a linear scan, right? Linear scan of the thing, right? So we would use the API given to us, right, to read the elements, right? So we would start from index 0 and work our way all the way to the end of the array, right? And hopefully finding the target, right? So if we go out of bounds, we don't find that number, we return -1, right? Because it just means that number does not exist in the thing, right? This would be a linear time complexity, right? Which is not good enough for this problem, right? Because they've said that they wanted their solution and log of n, right? So we kind of have to spend a little bit more time thinking it through, guys, right? See, how can we do that, right? We see that they're looking for a log of n, right? And what search algorithms that we know can give us that time complexity that they're asking for, right? So, and also it also said that it's sorted, right? Okay. So we know we need somehow kind of need to apply binary search, right? So binary search is going to be crucial for this problem, right? Okay, how can we apply binary search though? We don't have access to the array, which is important, right? We don't have access to the array. Okay. Maybe we could build the array, right? Somehow we could keep calling the API, put it in auxiliary, data structure, right? Put all the numbers and then apply binary search over that data structure. But it wouldn't be good though, because we will take us O of n to build the array, right? Because we need all to include all the elements, right? So it would not be too efficient, right? So because we're going for the log of n, right? So we need to think it through. So we need to know, we already know that we're gonna apply binary search, okay? But we don't have access to the array. So how can we know the left and right boundaries, right? Those are things that are important for us to start applying binary search, right? We don't have the access to the array to just do 0 to the end of the array. We don't have that, right? So which is the reason why I'm saying that that's not good, okay? We need to do a little bit better. So how can we do it, God? How do we find the boundaries? So we know the left boundary could be the first element, right? It could be 0, right? Okay, but how do we find the right boundary though, right? That's the answer that we're asking ourselves. The right boundary is not easily accessible, right? Do we do a linear scan, find the boundary, right? But it would take a linear scan, which is not good, right? So how can we do better? Maybe we can, let me see, uh, exponentially increase the the boundary, right, that we're considering, right, um, each time, right, by doubling the size of the by doubling the right pointer, right, especially increasing it, right. Uh, that way, right, by exponentially, doing that, right, by doubling every time, we are increasing it not in a linear fashion, but we're doing it exponentially, which is gonna help us in keeping the log of n thing, right? Because we can go from 2 to 4 to 8 to 16. No, we go 2, 4, 8, 16, 32, 64, right? Because we doubling it every time, right? This is the beauty of it, right? We double it every time. And by doing that, right, by doubling, when do we stop, right? We stop doubling it every time, guys, right? By when we get the range that we're looking for, right? The range that's going to be good, right? So any number that's equal, that greater than or equal to the target, right, can be our upper bound, right? Right? Because we know zero, right? And we need to know where to stop, right? So for this example, right, it would be we still be stopping it. So let's say where we're stopping at, right? So let's say initially our search space, right, is this one, right? So we got our left pointer at the beginning, and then we put our right pointer here, right? And we don't know where to stop for the right pointer, right? So we check that it does not reside in this area, right? No, it doesn't, right? So now double the size, like double the window, right? So the search space, right? So whatever the one is pointing at. So for the example, right, it's one, right? Index one, right? Multiply by two, right? So now one times two equals this, right? Okay. So now this is the index two, right? So now search space is this. Okay. So now we see that three is still less, right? So we double it. So two, we go boom, boom, right? So now, because we do two times two equals four, right? So we go three, four, right? So index four is here, right? And then we get our search space, right? Which is from everything from this to this. We can do our boundary search, right? We're gonna find that number, right? So the upper bound value needs to be a value greater than or equal to the target, right? And this is how we can make sure that because we could know that that number is going to reside between those indices, right? From the left boundary to up to that number, right? The number that's the number that's greater than or equal to the target, right? So this is the main point of that, right? And after we found the boundary that we have, right, we can apply binary search over that to find the value that we're looking for, right? So it would be none. We would find that easily, right? So yeah, guys, see how doubling the right pointer every time really helps us in efficiently finding the upper bound that we're looking for. Right? That's kind of the main gist of this problem, right? So you can kind of think about it, right? For example, we can find, so let's say you're looking for a number like, 64, right? So instead of going, doing 64 iterations, right, to find it, right? Using that technique that I just told you guys, right? We can go from 2 to 4 to 8 to 16 to 32 and then 64, right? Which would be 1, 2, 3, 4, 5, 6, right? 6 iteration, right? Instead of doing 64 iterations to find 64, right? So this is how doubling it every time the right boundary, right, can help us and efficiently get to our destination a lot faster, right? So it's kind of the same concept when we divide our search space in half, when we do the binary search, right? We cut down search space in half, right? But for this one, we're doubling it every time, right? Doubling our search space every time, right? And then we're increasing it, right? So this is what makes this interesting, right? So that's why we're gonna do that, right? So let's quickly go ahead and do some kind of so one more thing that I want to go before I want to say to you guys before I move on, right? So um as we're removing the right boundary, right, we're also going to be updating our left boundary as well, right? Because for this example, right, we see that 9 does not exist there, right? And then we double 2, right? Left doesn't have to stay at the beginning, right? Right. you could also move the left boundary as well, right, to equal to whatever. So because we know it doesn't exist there, right? That doesn't exist between the range, right? So we can also update the left boundary to be where the right pointer is at, and then the right pointer moves as well, right? So we do a check, it does not exist there, right? And then we keep it, since it's increasing, right? We also increase the left pointer to wherever the left pointer is at, right? So we know it's gonna be residing because we know that it doesn't reside within that first partition, right? So let's check this other partition where we also update the left, right? It will still work if the left pointer stays at the beginning, right? And you could apply binary search there, it'll still work, right? But I'm just saying to make it more efficient, right? Because the array can be very, very big, right? We want our search space to be as small as possible. And this is one of the optimizations that you could add to your problem, right? So yeah, I hope you guys understood what I just said. So let's quickly go into it, right? So what we're gonna do, we need to find our boundary, right? So which is the main point. So initially, boundary, the left pointer equals 0 and the right pointer equals 1, right? So very small search space at the beginning. Then now we're gonna be searching for our range, right? So that we can start doing some kind of binary search over that range, right? So yes, so we're gonna do the right pointer, right? I mean to type range. All right. So while the value, right, that the right pointer is pointing at, right, the boundary, right, because the right pointer serves as the boundary, right. So while it's less than the upper bound, right, is less than the upper bound of our search space, right, is less than the target, right. That means, we need to keep doubling the right pointer, right. Okay. And then we said that we're gonna also move the left pointer, right, to equal wherever the right pointer was at before we double it, right? Increase our range, okay? So once we take care of that, right, if we found a range, right, we found the value that's greater than or equal to, we find the upper bound that's greater than or equal to target, right? We found that case, then we could start applying our binary search guide, right? Which is the beauty of things right now. So while the left is less than or equal to the right, are we gonna calculate a midpoint? So it's gonna be the left plus right minus left divided by 2. And then we're gonna do a check here, guys, which is the rear get the main element. If that equals target, we can return the midpoint, right? The middle element, right? So now that's not the case. We make the decisions to either go to the left or go to the right. Okay. So the middle element, if it's less than the target, then we know we need to continue searching on our right side, right? Okay, so after we do that, we return. So if we don't end up finding the target, right, we return -1, right? So the summary of this problem, right, is that we start off with the 0 and 1, right? So left boundary is 0. It's easy, and then we just put, right to be at, left plus 1, right? And then we look for our boundary here, right? And we don't do it in a naive way, right? We do it in a very smart way, intelligent way, right? When we double the right every time, right? Exponentially increasing it, right? The boundary, right? To be, double it every time so that we can we can find it a lot faster, right? And once we find our upper bound, right, which is any value that's greater than or equal to the target, right? So we find that first one, right? So that we find it and we stop and then we apply binary search over that range, right? To find that target value. And yeah, just as that, guys, as simple as it is, press run code for sanity check. Okay, I'm going to put this equal sign. Looks good. Let's press submit. Awesome, guys. We're able to pass all the test cases, guys. So I want to thank you guys for taking the time to watch the video. If you guys found value, make sure to give me a like. If you guys are new, make sure to subscribe because I'll be doing a lot of other videos just like this one. So I want to thank you guys for watching, and I'll see you guys in the next video.